The pop operation removes the top element from the stack, but we would also like to remove elements in other locations. For instance, consider the following stack 5, 6, 8. If we remove the element at index 2, the stack becomes 5, 6. In order to remove the element at index 2, or 8, we must first remove the elements at index 0 and 1. Let's save these elements in a stack called popped, so that we can push them back in after 8 is popped. Here's a demonstration. Here's the table view. First we pop 5 from the stack and push it to the pop stack. Then we pop 6 from the stack and we also push 6 to the pop stack. Then we pop 8, but instead of pushing it to the pop stack, we discard it. Finally, we dump the pop stack back into the original stack. As we can see, the result of removing index 2 from stack 5, 6, 8 is equal to the stack 5, 6. To stop popping at index 2, we can decrease the index by 1 every time we pop an element. When the index reaches 0, we pop and discard the top element and dump the popped elements back into the stack. Let's now try to precisely describe the pop operation. We need to keep track of the popped elements, so we first convert the pop operation to the pop index compute function, whose inputs are the stack, index, and the pop stack. Here's the conversion property. The result of removing index I from stack S is equal to the output of function pop index compute, where input stack is S, index is I, and pop stack is empty. We can describe the behavior of the pop index compute function in two properties. Property 1 says that the output of function pop index compute, where input stack is top rest, index is I, and pop stack is PS, is equal to the output of function pop index compute, where input stack is rest, index is I minus 1, and pop stack is top PS. Property 2 says that the output of function pop index compute, where input stack is top rest, index is 0, and pop stack is PS, is equal to the result of dumping stack PS to rest. Property 1 says that the output of the pop index compute function will stay the same, even if we move an element from the stack to the pop stack, as long as we also decrease the index. For example, let top be 3, rest be the stack 4, 5, I be 1, and PS be an empty stack. Then the output of the function pop index compute, where input stack is 3, 4, 5, index is 1, and pop stack is empty, is equal to the output of the same function where the input stack is 4, 5, index is 1 minus 1, or 0, and pop stack is 3. Let's check whether the left or top side of the equal sign is really equal to the right or the bottom side. We know that the output where the input stack is 3, 4, 5, index is 1, and pop stack is empty is equal to the stack 3, 5. We also know that the output of function pop index compute, where input stack is 4, 5, index is 0, and pop stack is 3, is also equal to the stack 3, 5. Since both sides are equal to stack 3, 5, the left expression is equal to the right expression. Property 2 says that when the index is 0, then pop the top element and dump the pop stack back to the original stack. For example, output of the function pop index compute, where input stack is 4, 5, index is 0, and pop stack is 3, is equal to the result of dumping stack 3 to stack 5. Again, the expressions on both sides of the equal sign are equal to the stack 3, 5. As another example, let's evaluate the result of removing index 2 from stack 11, 19, 17, 23. First, we can use the conversion property to claim that the result of removing index 2 from stack 11, 19, 17, 23 is equal to the output of the function popIndexCompute, where the input stack is 11, 19, 17, 23, index is 2, and pop stack is empty. Now let's use property 1 to claim that the output of function popIndexCompute, where input stack is 11, 19, 17, 23, index is 2, and pop stack is empty, is equal to the output of the same function, where the input stack is 19, 17, 23, index is 2 minus 1, and pop stack is 11. Since 2 minus 1 equals 1, we can substitute 1 for 2 minus 1. Use property 1 again to claim that the output where the input stack is 19, 17, 23, index is 1, and pop stack is 11, is equal to the output where the input stack is 17, 23, index is 1 minus 1, and pop stack is 19, 11. Since 1 minus 1 is 0, we can substitute 0 into 1 minus 1. Since index is 0, we can now use property 2 to claim that the output of this function, where the input stack is 17, 23, index is 0, and pop stack is 19, 11, is equal to the result of dumping stack 19, 11 to stack 23. Well, we know that this is equal to the stack 11, 19, 23. Now we can use the transitive property a few times to conclude that the result of removing index 2 from stack 11, 19, 17, 23 is equal to the stack 11, 19, 23.